Wearable devices, such as smartwatches, are getting increasingly popular because they function not just like a traditional watch. They also record important health information, such as one's heart rate and blood pressure, while we are doing our everyday activities. However, if you do wear a smartwatch, just like I do, I'm sure you often come across the frustration of your wrist getting sore after wearing it for the whole day. This is because most of the wearable electronics are made from inorganic semiconductors, and they are planar and rigid, while our biological tissues are 3D and soft. To overcome this discrepancy, my PhD work used high-precision 3D printers to fabricate 3D structured microfluidic and electronic devices with organic materials. The challenge of 3D printing microfluidic devices is that the ink flows before it completely solidifies. Imagine that you are trying to squeeze an entire tube of toothpaste and stack the fresh filaments to build a hollow channel. Most likely, the structure will collapse under its own weight. What I discovered is that there is a critical stacking angle and dimension that allow the printing of microfluidic channels with such materials. Then, I programmed the motion of the printer head and printed microfluidic networks on curved surfaces. This gives us a powerful tool to control and manipulate the liquid flow on biological surfaces. For instance, customized microfluidic tattoo can be directly printed on human skin. This tattoo can wick the body fluids such as sweat for physiological analysis without even being noticed. By the same token, I printed organic photodetectors on curved surfaces to mimic the function of biological eyes. This spherical photodetector ray can detect light patterns with a wide field of view, just like what a human eye does. Once printed on soft substrates, this bionic eye can be implanted in human eyes and help restore the vision of patients who are suffering from retinal diseases. Most importantly, these two different systems, microfluidic and electronic devices, can be seamlessly integrated on 3D printers to form a concise and hybrid sensor. By guiding the solutions to flow across the sensing array, the sensor converted the biochemical information of the analytes into electrical readouts in a real-time manner. With these developments, I'm very excited to see that we're getting so much closer to the next generation wearable devices. Thank you.